Hi, in this video I'm going to show that when we have a Bayesian inference problem and we have both a Gaussian prior and a Gaussian likelihood, then in the previous video I showed we can use the multiplication rule for Gaussians, and here I'm going to show we can also use the fact that when we do conditioning and marginalization over a joint Gaussian, we're going to end up with Gaussians again. Going to do that on my iPad again. So let's say I have a variable z, and z is just a vector, and I've grouped a bunch of components in x and a bunch of components in y, and z is just a joint Gaussian. So I can write it as a distribution over z with mean vector mu and covariance matrix sigma. But because of the partitioning in x and y, I can also write it like this now. So it's a distribution over x, y, and the mean vector can be partitioned in mu x and mu y, and the covariance matrix in mu x, y, mu yx, and mu y. Note that since variance matrices, covariance matrices are always symmetric, that sigma yx is also the transpose of sigma xy. Now we can ask the question, so can I also split now pz, because pz is really the joint over y and x, into the conditional py given x and the marginal px. And indeed, there are analytical answers for this. They are derived in Bishop. It's not an easy derivation nor a short derivation, so I'm not going to do it in class, but you can read about it if you want. And the answer is that for marginalization, there's a very simple answer. So the marginal for x is a distribution over x given mu x sigma x, where mu x and sigma x, I mean of course this mu x and this sigma x. So that's really easy. The formula for py given x, I can also express it as a Gaussian over y, of course, with a mean and a covariance, and they're analytical answers, but unfortunately the answer is not very simple. The formula is going to be mu y plus sigma yx sigma x to the power minus 1 x minus mu x, and for the covariance sigma y minus, and now I hope it's going to fit, sigma yx sigma x minus 1 sigma xy. Ooh, that almost didn't fit. Anyway, this is the covariance and this is the mean for p of y given x. So they're terrible formulas, right? On the other hand, if we take a look at this new mean, it's you kind of recognize this prediction correction thing again. The marginal for py would of course be just a Gaussian over y with mean mu y and variance sigma y. So the predictor, if I haven't observed x yet, the predictor for y is mu y, and the predictor for x is mu x. So what this formula tells me is that the posterior, or let's say the posterior for y given x, consists of the prediction of y in absence of any measurement, plus a correction term after I make a measurement, which is the prediction error. Mu x is what I really thought x would be, but it turns out it's going to be x when I make the measurement, so I have prediction error. I weigh it with the precision for x, and then I project that onto the, let's say, onto y. So you can kind of talk your way through this formula. If it's enough to remember the formula, I don't know. You don't need to remember it because these formulas are in all books and tabulated. So in the same way, what we can say about this new variance is that, well, sigma y was the variance before I saw x, and this is the variance conditioned on x after I make the measurement. And after I make a measurement, I get more information. So it's good to see that the variance decreases, right? I used to have sigma y and I subtract something. That's these are analytical results, and we can use that, right? Because it turns out that in the same problem that I had before, namely the problem was I had this system with a particular likelihood. There's formulas. Now I go back to the problem of estimating a posterior for theta based on a measurement x. So the likelihood was a Gaussian over x given theta sigma squared, and the prior for theta was a Gaussian over theta mu 0 and sigma 0 squared. That's my prior. This is something we did in the previous video. Now I can rewrite this, right? I can say, okay, let z equals the joint, or basically the vector x and theta, and I just put them together. And it turns out, and this is a bit of an exercise, but you can calculate, or you can write out now the probability distribution basically for the vector x theta. That's a Gaussian, of course, over x theta. This is a theta with mean mu 0 and covariance matrix mu 0 squared plus sigma squared, sigma 0 squared, sigma 0 squared, and sigma 0 squared. So this is my covariance matrix. This you can basically compute by the definition of what is a covariance and what is a mean, and then just take out the information out of this model. It's a bit of an exercise, but it's a really good exercise to do it. So that's why I'm not going to completely work that out here. I would like you to try to derive this. Now, once you have derived this, it's basically going to be straightforward to compute the posterior. The posterior for theta given x, because, well, that's just straightforward this formula, right? I just have to do the formula in this case for py given x. I can just immediately fill it in. I'm going to get a Gaussian. No, let's just first take for the mean. So the mean, the posterior for let's say this is n over theta mu 1 sigma 1 squared, and mu 1, and I'm looking at this formula here. Mu 1 is going to be, I have to take mu y, and mu y is mu 0. Mu 0 plus, and I have to take now this, this guy divided by this guy. And I have to multiply that by x minus mu x, which in this case is going to be x minus mu 0. So this formula is it basically is the same formula as this formula. It's the same formula as this formula. I just take it straight, just fill in straight the formula. You see that you get actually now an answer that immediately has this predictor corrector term, but in whatever form you get, it's the same answer as we had before. I can go back to the previous video and you'll see here exactly the same formula. So, however, you can do it in many ways. Bayesian inference, you can use the formulas for conditioning and marginalization. You can use the formulas for multiplication. They come out in the same way. They're just examples of Bayesian inference with Gaussian prior and Gaussian likelihood, that combined with the fact, some scientific facts, some information theoretical reasons why it's a good idea to use Gaussians, makes this for a really nice framework for doing inference on continuously valued data. So I think I'm going to stop here. I don't want to make it too long, so please read the lecture notes and let's discuss the questions you have in class.